Hello, everyone, and again, thank you all for joining us on this Friday. Happy Math Hour. We'll give a couple of seconds for those who are here for the 1324. Again, the link is now posted in the chat. So if you're here to review Math 1324, go ahead and click on that link to go into that session. All right, very good now. So today's Happy Math Hour, we're going to be dealing with exponential and logarithmic functions. So let's first explain what an exponential function is. An exponential function is defined as an equation that has a base, okay, and denoted as a in this example, and the subscript is known as our exponent. Okay, so a has to be greater than 0, and a is not equal to 1. Okay, so the domain of an exponential function is a set of all real numbers, while the range is a set of all positive real numbers. All right, so let's look at some basic properties, and this is to help us graph. Okay, so I like to think of this equation y equals a to the x as our parent function or parent equation, and this graph has a y-intercept at 0, 1. When x is equal to 0, y is equal to 1. Okay, the graph is continuous. And the continuous again means that there's no holes or jumps or breaks. The x-axis is what's called our horizontal asymptote. We've covered asymptotes before. This is the imaginary lines that a graph cannot cross or touch. Okay, so if a is greater than 1, then we say that the exponential equation is increasing. If a is between 0 and 1, meaning a fraction, then a is decreasing as x is increasing. Okay? So let's look at the graph. Okay? So again, this is what I like to consider my parent function. From this graph, we can graph any exponential function. So this is what we just covered. Our domain is from negative infinity to positive infinity in interval notation. Again, the range is all positive real numbers. So this is from 0 to positive infinity. We have our y-intercept at 0, 1. And this graph is increasing, right? If we read the graph from left to right, we see that the graph keeps going up and up and up. Okay. So again, it's not labeled here, but at x equals 0, we have a horizontal, at y equals 0, we have a horizontal line that is our asymptote. And usually we label our asymptotes as a dashed line, but again, we can't see it here. And again, our graph is continuous. That means that there's no breaks, holes, or jumps, yes? All right, so if we were to plot a few points for our exponential graph here, again, this is our parent function, f of x is equal to 2x. So as I put values into it, if you see, if we have negative values, we see that our output are fractions, right? These are the values between, we're talking about 0 and 1, right? And then when our values are greater than 1, then they start increasing much rapidly. 2 to the 1, 2 to the 2, 2 to the 3 would be 8, and so on and so forth. So this graph increases very, very quickly. So when we have negative values, as you saw on our table, okay, we can rewrite 2 to the negative x as 1 over 2 to the x. These two forms of the function are the same thing. One is just an exponent form with a negative exponent, and the other one has its positive, right? We take the reciprocal of the function and we change the sign. So on this particular graph, it has a reflection on our y-axis. So our domain did not change. It's still from negative infinity to positive infinity. Our range did not change either. It's still from 0 to infinity. We still have our y-intercept at y equals 1. But now it's decreasing. Again, when we read graphs, we read them from left to right. Then we see that our graph is going down, right? So as it's going down the graph. Our horizontal asymptote still hasn't changed. It's still at y equals 0. It's a horizontal line. And this graph, again, is continuous. So let's look at some of our properties for exponential functions, or our laws. So the first one that we see here is our product rule. When we have two exponents that have the same base, and we're multiplying them together, we're going to add the exponents. So inversely, if we have two exponential equations that we're dividing that have the same base, we will subtract the exponents. Okay. Then we have so the first one was our product rule or product law. The second one was our quotient rule or quotient law. Then we have our power rule, that if we have an exponential function and we take it to another exponent, we multiply the exponents. Okay. And if we have more than one value as far as a power, again, we have to take that exponent to every single value inside. Okay. Same thing if we were dividing. If we're dividing a over b to some power, that's the same thing as a to the x divided by b to the x, to that same power. Okay. So here, this rule 2, we like to call this our one-to-one property. For two exponential equations to be equal to each other, okay, that means that the bases have to be equal and the exponents have to be equal. And if we have that, if we can match that, we call that our one-to-one property. And we're going to use this a lot, especially when solving equations. One way to solve equations fairly easy is using this property, our one-to-one property. So let's put it to use. Okay, let's solve this equation. 10 to the power 2 minus 4x is equal to 10 to the power 6x minus 1. So can we use the one-to-one property? The answer would be yes, because I have two exponential equations that have the same base. So because they have the same base, and for these two equations to be equal, that means that their exponents all have to be equal. So if I want to solve for x, I'm going to set these equal to each other. 2 minus 4x is equal to 6x minus 1. Again, these are just the exponents. And now I just have to do algebra to solve. Again, I like to move the x's to the left and the constants to the right. So when I do that, I get negative 10x is equal to negative 3. Divide both sides by a negative 10, and x is going to be equal to 3 over 10. So again, we will be using our one-to-one property a lot, especially to solve equations. And you can see, it makes our life really easy. So let's look at this example. Can we use the one-to-one property on this case? Well, at first glance, you might say no, because the right number is just a number. It's not an exponent. But we can convert that 64 into an exponent. Now we can pick several bases for it, but what we want to do is we want to use our one-to-one property. We want to have a base of 4 in order for us to use our one-to-one property. So yes, we can convert 64 into something that has the same base. So 4 to the third power. 4 to the third power will give me 64. 4 times 4 is 16. 16 times 4 will give me that 64. Now I see that I have two exponential equations that are equal to each other that have the same base. And for these two equations to be equal, the exponents also have to be equal. So I'm going to set the exponents equal to each other. So this means that x plus 1 has to be equal to 3. And it's easy now to see that x would be equal to positive 2. Yes? So subtract 1 on both sides, and x will be equal to 2. Okay. Yeah, and if you have any questions, or if I'm going too fast, I do want to cover quite a bit of material. Again, we're in the summer session, so we cover a lot every day, right? But if I'm going too fast, please let me know, raise your hand, or put it on the chat. Let's look at this next example. 5x minus 3 is equal to 1 over 125. So I can solve this using my one-to-one property. I can first, again, a step that I took out was I can write 125 as an exponent. That's 5 to the third power. But because I want it to be a base, I take the negative reciprocal of that, and that's going to become 5 to the negative 3. So now you see that I have two exponents that have the same base. So I can apply my one-to-one property by setting my exponents equal to each other. So x minus 3 is equal to negative 3. So x is equal to 0. Okay. All right. Now, when we're looking at exponential functions, a very popular base to use is this e. And e is a symbol, just like pi is a symbol that represents a number. Pi represents 3.14. Well, e is also a symbol that represents an irrational number. Okay, and this number is 2.7182. Again, irrational because it never ends, it never terminates, it never repeats. It just goes on forever, right? So we call this the natural base, and we use this a lot for business. We like to use this base e for business, and then it's called the natural exponent. Okay, believe it or not, it's going to have the same graph as my parent function for science, or the one that we saw was f of x is equal to 2x. This is the same graph, okay? Even though we're using a different base or a different symbol, it still produces the same graph. It's a continuous increasing graph, okay? It still has a y-intercept at 1, okay? And again, it's continuous, doesn't have any breaks or jumps. All right, so we can use this and also still apply our one-to-one property. So here, if we wanted to solve for x, we have two exponential equations and they have the same base. Both of them have a base of e. So for these two equations to be equal, the exponents must also be equal. So applying my one-to-one property, I'll set my exponents equal to each other, which is x squared minus 3 is equal to 2x. Uh-oh. So I have a quadratic to solve, right? So if you notice, we have an x squared value. So what I'll do is I'll move everything to one side to have a quadratic equation. We have x squared minus 2x minus 3 is equal to 0. So again, you can solve for x several ways. You can factor. You can use a quadratic formula. I don't know about you, but I like to use the factoring technique, yes? So if I factor x squared minus 2x minus 3, this factors into x minus 3 times x plus 1 equals to 0. Now I use my 0 property that for these two products to equal to 0, either x minus 3 is equal to 0 or x plus 1 is equal to 0. And this will show me that x is equal to 3 and x is equal to negative 1. Okay, now it's a good rule, especially when you're doing homework, is to double check these values. Make sure that the values give you a solution, okay? All right, so now let's look at logarithmic functions. So believe it or not, logarithmic functions are the opposite of exponential functions, or the inverse of exponential functions, okay? So we write a logarithmic. We don't write this long word, okay? When we're writing it in an equation, we just use log for logarithm. Now, logs also contain a base. Instead of a number, it's a subscript now. So the b represents a subscript, okay? So an equivalent format to this log is its exponential form. So the way I like to think about it is as an input and output, like the way we taught you functions. So see, in my log, for these two to be equivalent, we have to have the same base. But the input of the log becomes the output of my exponential. The output of the log becomes the input of the exponential. That's what makes them inverse of each other. They're the opposites, yes? So, and they're opposites in every format. If you remember, the domain of the exponential function was from negative infinity to positive infinity in interval notation. Now the domain for the log function is just the positive values from 0 to positive infinity. That was the range of the exponential function. And the range of the log is um, from negative infinity to positive infinity. And that was the domain of my exponential function. So they're opposites of each other, or inverses. So if we look at the graphs back to back, okay, again, the exponential function has a y-intercept and a horizontal asymptote. The logarithmic function has an x-intercept and a vertical asymptote. This one has a vertical asymptote at x equals 0, okay? So let's look at some of our common logs, okay? Whenever you don't see a base or a number, a subscript for the log, we automatically assume that we're dealing with a base 10, okay? Now, the natural log, that's already in base 10, okay? So here, the natural log of x is the same thing as the log of e to the x, okay? Now, one of the ways to solve logarithmic equations, or the easiest way to solve logarithmic equations, is to convert them from logarithmic to exponential. Of course, we can solve any exponential equation, but logs are a little bit harder because if you know, our calculators have a log button, but they only solve logs that have base 10. Because again, we only have 10 numbers for counting, right? The 0 through 9. But in this case, we have a log of base 4. So to solve this, what I'm going to do is convert this log equation into its exponential form. So again, I see the base of this log is 4. So the base of my exponent will be 4 as well. Oops, went too far. So here, as before, the output of my log is the input of my exponential. The input of the log is the output of my exponential. For 4 to the x is equal to 16. How do I solve this? Well, now I can solve it using my one-to-one property as well. I can convert the 16 into an exponent, and I can say that 16 is the same thing as 4 squared, so x has to be equal to 2, okay, if you didn't see it. How about this one? 125 is equal to 5/3. Let's do the opposite. Let's go from exponential to log. Again, the base of this exponential is a base 5, so that means that my log also has to have a base 5. The input of the exponential is the output of the log, and the output of the exponential is the input of the log. So 125 equals 5 to the third power in log form is log of base 5, input 125, my output is 3. Okay, let's look at another example. What about this one? Log of base b, 27 is equal to 3. Let's convert it into exponential form. So the base of this log is just b. It's not a number, it's just b. So that also has to be the base of my exponent. The output of the log is the input of the exponent, so it's b to the third. The input of the log is the output of the exponent. So it's b to the third power equals to 27. Okay, and again, we'll use this a lot to solve some of our logarithmic equations. All right, how about this last example? The square root of 81 is equal to 9. Let's convert this into a log expression, right? So you may not see it, but we can convert the square root into an exponent value. The square root of as an exponent is to the 1/2 power, right? So we have 81 to the 1/2 power is equal to 9. So now I see that my base is 81. So my log has going to have a base of 81. The input of the exponent becomes the output of the log, which is equal to 1/2. The output of the exponent that was 9 now becomes the input of the log. So it's log of base 81. I enter 9. My answer is going to be 1/2. Okay. All right, so let's look at some of our basic properties that will also help us solve some of our equations that we're going to be looking at. Um, so as I had mentioned to you, the common logarithmic function is a base 10. That's the one that your calculator will be able to do. And again, it's denoted by the log button. Okay, but let's look at some basic properties. So first of all, the log of any base, and when I put 1 into it, okay, the answer is going to be 0. Inversely, any exponent, when I input 0, the output is 1. As you can see, they're opposites of each other. The second one, it's like our identity property, right? If I have a log of base a and I input a, the answer is going to be 1. The exponential form of this, a to the 1, is just a itself, right? The third property here, log of base a to input a to some exponent. Well, it's kind of like our power rule. It's just x times the log of the 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 log, but log of base a to input a, that value is 1 from our first property, right? So our answer is just going to be x. And then the last property, if log of base a of x is equal to the log of base a of y, now what that's saying is that it's my one-to-one property, that for those two logs to be the same, if they have the same base, then the inputs have to be the same. Okay, so let's look at some of these examples as problems. Use properties to solve. All right, so here, what I would do is I'm gonna go ahead and convert this into an exponential form, because Again, I don't know how to solve it. Again, my calculator only does log of base 10, but I can use my properties to solve. So let's look at converting it to exponential form. And again, I think this is the easiest and fastest way to solve these problems. So again, here I have a log of base 3, input 127. So then my exponent here has to be, my base for my exponent has to be 3. The input of the log becomes the output, and what I don't know is the output of the log, which becomes the input of the log. Well, what I can do is I can use my 1-to-1 property. Can I convert this 1 over 27 into something that has a base 3? Well, the answer is yes, right? So 127, or the 27, I can write that as 3 cubed. But if I want it as a base, I do the negative reciprocal, and that's going to give me 3 to the negative 3. Now it's very easy to see that for these two equations to be equal to each other, what's my question mark? The answer would have to be negative 3. Yes? So that is my answer. And again, and I did this by first converting it to an exponential form and then using my 1-to-1 property. All right. So let's look at the properties that we use to solve this again. Okay. So if we look at this, we first wanted to get a base for my 3. So it's 1 over 3 cubed. Okay. I did the negative reciprocal to make it into the top. Yes. So I have log of base 3 to the negative 3. I can use my power rule saying that I just multiply this negative 3 to my log. So that's going to give me negative 3 times the log of base 3 to the 3. And then I can see that I can use this property here, that if I have a log with the same base and I'm inputting the same value, the value is just going to be the exponent. So you can see that my value here is just, my answer is still negative 3. Okay, so those are the two ways that we can use to solve these problems. All right, let's go ahead and solve this one. Use properties to solve. Log of base pi to pi to the 5th power. So hopefully with that previous example, we know what the answer is just by looking at it. And you can see we're going to use the same property that we use right now, that when we have a log of given base and we're inputting that same value as an input, the answer is just the exponent. So on this one, our answer is just going to be 5, right? Okay. How about this one? Log of 7.5. I'm going to give it an input value of 1. Well, this one's hopefully, if I know my properties, I don't care what the base is. That base could have been whatever number. I know that the answer is going to be 0, because anything, any log to an input of 1 is just going to give me 0. All right, how about this one? Log of 90 to the input 90. Oh, this one's that first property, right? Sorry, second property. That a log of a given base and I've input the same value is just going to give me the answer 1, right? So it's that second one. So our answer is equal to 1. How about this last one? 3, and I have an exponent to the log of base 3 of 8. So you can think of this as like my inverse property, right? This log of base 3 is going to cancel with the exponent of base 3. And what's going to give me the answer is just the input, which is still our inverse property is our property number 3, right? But for logs. So what's going to be the answer? The answer is just going to be 8 on this one, right? All right. So let's go ahead and look at some more examples. Using the definition of logarithms, can you solve the given equation? So let's go ahead and do it. We have log of base b of 1000 is equal to 3. Well, let's see. Let's rewrite the 10,000 as, or the log of base b of 1000 equal to 3. Let's convert it into exponential form. So my base of my exponent should be b. The input of the log, it becomes the output of the exponent, and the output of the log is the input of the exponent. So b to the 3rd is equal to 1000. So I hope that we can see that the value for b, in order for me to get 1000, the answer should be 10. 10 cubed is going to give me that value. 10 times 10 is 100. 100 times 10 will give me the 1000. Yes? So again, it's this form to solve equations. the easiest and most common way to always do it is to convert it into exponential form. All right. Let's look at some more properties. Okay. Um, so let's look at first we looked at 1 through 4 already. Now let's look at 5, 6, 7, and 8. So again, the first one here is like our product rule that says that when we have a log of a given base and we have two elements that are being multiplied within that log, I can expand it into two separate logs. So the log of base b of m times n could be written as the log of base b of m plus the log of base b of n. And you can think of this as your product rule for exponents. Like for instance, if I was multiplying x squared times x squared, you know that you add the exponents. The answer would be x to the fourth. This kind of has the same property for logs. When you have two things that are being multiplied, you're going to add the logs. So inversely, division, the division of two elements with the same log. So if I have log of base b, m divided by n, that can be expanded to two logs. And opposite of addition would be subtraction, right? Log of base b of m minus the log of base b of n. And that has the same rule as the exponents. If I was dividing x squared by x, to get the answer, I subtract the exponents, right? That would be 2 minus 1 will just give me x. So it has the same properties, right? Because they're inverses of each other. How about 7? 7 again is the power rule, that when I have a log of base b to a given input, that exponent, we just multiply it to the log, okay? Same thing if I had an exponent to another exponent, you multiply the exponents, okay? And then the last one, number 8. And this is our one-to-one property. For log of base b of m be equal to log of base b of n, that means that, again, they have to have the same base. And if they have the same base, they have to have the same input. That means that m and n have to be equal to each other. Okay. All right, so let's look at some examples using our logs. So here we have log of base 5 of x plus 1 is equal to log of base 5 of 9. So on this particular problem, what I can do to solve is using my one-to-one property. I have two logs that are equal to each other. They both have the same base. So in order for these two logs to be equal to each other, then the inputs must be equal. So I'm going to set my inputs equal to each other. So it's going to give me x plus 1 is equal to 9. Solving for x, x will be equal to 8. Yes? And again, it's my last property here, which was my one-to-one property. All right. Let's see. Let's look at this one. Log of 17 equals to the log of x squared plus 8. So again, keep in mind, when they don't write a subscript down there, that means that our base is 10. Okay, so when you see a subscript, we automatically assume that it's our base 10. So these two logs that are equal to each other have the same base. It's a base 10. So again, I'm going to use my one-to-one property. The inputs also have to be equal. So then I'm going to have 17 is equal to x squared plus 8. Okay, what I can do is, again, I have a quadratic equation to solve. We can factor, we can use our quadratic equation. Again, my go-to method is always to factor it out, right? So we first combine our like terms. 8 minus 16 gives me the negative 9. I know I can convert this into a difference of squares. So this is the same thing, or we can solve. Okay, again, there's several ways. I'm going to use my square root property then to solve. Take the square root of both sides, and this is going to give me the square root of 9, which is going to give me plus or minus 3. And again, I would have gotten that with a difference of squares. Difference of squares is x minus 3, x plus 3. The x values are 3 and negative 3, right? And again, you always want to check your solution. You want to make sure that the values, the answers that you get, satisfy the equations. Okay. So if we plug these in, again, when we plug 3, positive 3, we see that we get the both sides are equal to each other. And when I plug in a negative 3, both sides are equal to each other. But this will not always be the case, okay? So please always check your solutions. You may have two solutions sometimes, but maybe one of them does not work. So always please check your solutions. All right, let's look at this one. Can I apply my one-to-one property? Well, the answer would be yes. This is the natural log, Okay, the natural log is the same log, and again, the natural log works as a base 10. It's like my exponent e. So I'm going to use my 2-1 property, and I'm going to, for these two logs to be equal, my inputs have to be equal. So x squared minus 3x is equal to 18. Again, we're going to end up with another quadratic. X squared minus 3x minus 18 is equal to 0. I am going to factor this out. X minus 6 times x plus 3. So my values are 6 and negative 3, right? So these are my solutions. But again, let's check. We've got to make sure that if we have two answers, both answers are going to work. So let's look at this next example. We have log of base 4 of x plus 6 plus the log of base 4 of x minus 6 is equal to 3. Well, what we can do is we can condense the left side to make our lives a little easier to solve this problem. Oops. So I don't have the work here for us, but the way I would do this one, let me pull out my pen really quick. You see here I have two logs that have the same base and they're being added. So this is the same thing as the log of base 4 of x squared. Well, actually not factor it out. Let me should have put it together. Eraser. Here we go. Let me write it first. I was going to give you an answer, but let me write it first. X plus 6 times x minus 6 is equal to 3. And now when I have it in this format, again, I can convert this into an exponential form and solve for x. Yes? All right. Let's go ahead. Let's solve for this one. Log of base 5 of 125 is equal to x. Okay. Again, I don't want to solve it using logs. Let me go ahead and convert it to exponential form. So what I'm going to do is I have a log of base 5. So that means that my exponent has going to have a base 5. The input of the log becomes the output of the exponent. The output of the log is the input of the exponent. If you don't see what the x is equal to, you can use our 1-to-1 property. I can convert 125 into something that has a base of 5, and that is 5 cubed. 5 cubed is 5 times 5 is 25. 25 times 5 is 125. So it's easy to see that the value for x is equal to 3. Okay. And hopefully you see the problems are this easy if we apply some of our properties and conversions. All right, how about this one? Log of base 2, 25 is equal to x. Let's go ahead and convert this into an exponential equation. So if we convert, we have a base 2, so our exponent has to have a base 2 as well. The input of the log has to be the output of the exponent. The output of the log is the input of the exponent. But 25, can I make that into a base 2? Well, the answer would be no, right? So we can't use our 1-to-1 property for this. So we would have to use a calculator in order for us to solve for this one, okay? All right, so again, we can plug it in if your calculator allows you to change the base, okay? You would do the log of base 5 and input those values. So these are pictures of examples on how it would look to solve for a problem like this, okay? Now, one way you can do it if your calculator does not have a feature to change the base, what you can use is the change of base formula. That says that if you have a log of a given base and your calculator only does log of base 10, what you can do is you take the log of the input, which would be, it would have a base 10 log, divided by the log of the base, and that will give you the same solution. Okay, it's a change of base formula. So let's look at some examples using the change of base formula. I have a log of base 3 of input 11. So if I want to use my calculator to solve A, the way I would do it, it would be the log of base 10 of 11 divided by the log of base 10 of 3. This ratio, again, in the computer and web design, they're not going to change. They're not going to tell you use a change of base formula. They're going to tell you convert into a ratio. Okay, and what they're talking about is this: is converting it into a fraction. the log of 11 by the log of 3. Okay, and then when I do that in my calculator, the answer is going to be 2.183, and this is rounding to the thousandths place. Yes. How about this B? Log of pi input 0.5. So the way I would do this one, it would be um, the log of base 10 of 0.5 divided by the log of base 10 of pi. Again, this is going to give me a negative answer. It's going to give me negative 6.06. Okay. All right. So again, these are some of the properties summing up what we looked at. So some of the things that we can use is to expand our logs, and let's practice with this one using just numbers. You have a homework problem that says use properties of logs to rewrite the logarithm in terms of log of base 5 of 2 and log of base 5 of 3. Okay, so what I can do is, because they want an input of 2 and 3, can I make this 6 to have a product of each other? And the answer would be yes, right? 6 can be rewritten as 2 times 3, right? 2 times 3 is 6. Now I can use my product rule to rewrite as the homework is asking me. Since they have a base 5, I can expand it to have log of base 5 of the input 2 plus a log of base 5 of the input 3. Okay, and I use my product rule to solve for that. All right, how about this one? Find the exact value of the logarithmic expression without using a calculator. Easy stuff, okay? So one way to do it is, first, let's go ahead and convert the log, the input, into an exponential value. That we have a cube root. I can write that cube root as 4 to the 1/3. I can use my power rule because I have an exponent that's going to give me 1/3 times log of base 4 to the input 4. And I know that I got my identity property that any log with a base of 4 and the input is 4, that value is 1. So 1/3 times 1 is going to give me 1/3. Yes. And I was able to solve this problem without using a calculator. And also be careful, guys, on WebAssign. Okay, WebAssign will know if you're using a calculator. So if you're putting in decimals as answers for these, they're gonna mark them wrong. They want the fraction format. Okay, they want the exact answer. All right, let's look at these. Look at some more without using a calculator. Okay, so let's look at the first one. Natural log of the 4th root of e to the 3rd power. So the first thing that I want to do for a is convert that 4th root into an exponential form. That is e to the 3rd to the 1/4. I can use now my power rule, and that's going to give me the natural log of e to the 3/4 power. Now I apply my power rule, and that's going to give me 3 to the 4th power times the natural log of e, and I know the natural log of e is 1, so my answer is just going to be 3 to the 3/4. Yes, 3/4. All right, let's look at b. The natural log of e to the 4th plus the natural log of e to the 8th power. Okay, so first I'll apply my power rule for both. Okay, so this is going to give me 4 times the natural log of e plus 8 times the natural log of e. Okay, so what I can see is here we can use our properties to solve this. That for these two to be, since I have the same natural log of e and natural log of e, again, that's 1. So 4 times 1 plus 8 times 1 is just going to give me 4 plus 8, and 4 plus 8 is equal to 12. Okay. All right. Let's look at this one. Use properties of logs to expand the expression as sum, difference, and or constant multiples of logarithms. So again, what they want us to do is go from one log to many logs, right? And we're going to use our properties for that. So I have this example. I have the natural log of z times z minus 1 to the 4th power. So the first thing that I notice is that I have a log and I have two things that are being multiplied with each other. So I can use my product rule. I can expand this first by saying that I have the natural log of z plus, oops, I forgot the natural log there. There's supposed to be a natural log here. Let me put it in. There should be an ln here, okay? Natural log of z minus 1 to the 4th power. Um, then apply my power rule. Oh, there it is. Now it appeared. Um, we missed it on one of the slides. All right, so we have natural log of z plus 4 times the natural log of z minus 1. And I'm done. I cannot go any further. I expanded. I went from 1 log to, on this particular one, 2 logs. And again, we want to get rid of all of our exponents because the problem says constant multiples of logarithms, okay? All right, I like this one. Let's expand this log. Log of base 5 of the square root of x squared minus 9 divided by 4, okay? So the first thing that I see that I have a log of base 5 and the input has a division, right? There's a fraction. So what I'll do is apply my quotient rule. This can be expanded to the log of base 5 of the square root of x squared minus 9 minus the log of base 5 of 4. Oh, but I can rewrite the square root as an exponent. So let's go ahead and do that. Let's rewrite the square root as the power of 1/2. So now I can apply my power rule. So this is going to give me 1/2 times the log of base 5 of x squared minus 9 minus the log of base 5 of 4. But guess what? We are not done. We can rewrite this as a different format. This x squared minus 9, this is a different squares again. It's another example of difference of squares. I can rewrite that as x minus 3 and x plus 3, okay? This is this factor. So now you see that I have a log of base 5, that I have two things that are being multiplied. Now I can apply my product rule. So the final answer for this one is going to be 1/2 log of base 5 of x minus 3 plus 1/2 log of base 5 of x plus 3 minus log of base 5 of 4. Okay, don't forget to carry the 1/2. Since the 1/2 was multiplied to this whole one, I have to multiply the 1/2 to both of the product rules. Okay, do not forget those halves. All right, let's look at more examples. Let's look at A. We're expanding. We're still expanding. Let's expand the log of base 8 of x cubed over y cubed times z to the 4th. So the first thing we see is we see a division. We're going to apply a quotient rule. So this is going to give me the log of base 8 of x cubed minus the log of base 8 of y cubed z to the 4th. Let's go ahead and apply my product rule for the second part. I have a log of base 8 that I have two things that are being multiplied with each other. So let's go ahead and do that. Now, be very careful. When we have a negative and we have some more stuff going in on the right side, we want to use parentheses so we can keep the order of operation. Because if we don't put those parentheses, if we were to work backwards, we're not going to have the same equation that we have started. So we have to give order of operation. So don't forget these parentheses. So in these parentheses, I have log of base 8 of y cubed plus the log of base 8 of z to the 4th. So I'm almost done. I have exponents. So I'm going to apply now my power rule. So applying my, I can also distribute. So if you leave it on the homework on the computer, I think it's going to accept this answer. But just in case, let's go ahead and distribute our negative. And this is going to give me log of base 8 of x cubed minus log of base 8 of y cubed minus the log of base 8 of z to the 4th. And by distributing, we don't have to worry about the parentheses or the order of operations. Now we work backwards, it's going to give us the problem that we want. But again, so we're not done. The last thing is applying our power rule to get rid of our exponents. So anything that has an exponent, we're going to multiply it to the log. So we're going to get 3 times the log of base 8 to the x minus 3 times the log of base 8 to the y minus 4 times the log of base 8 to the z. Okay, let's look at B. We have the natural log of this big square root. So the first thing we want to do is let's go ahead and rewrite the root. So this is a 10th root. Let's write it as an exponent. We write this as an exponent. It says 1 to the 10th power. Now I can apply my power rule. And it's going to give me 1 to the 10th power times the natural log of this long problem here. As you can see, I see two things that are being multiplied with each other. So what I can use is my product rule now. So my product rule is going to give me 1/2, and I'm going to use parentheses. I can distribute my 1/10 later. So I have natural log of x to the 7th plus the natural log of x to the 5th plus 7. Like I said, I think you can leave the answer like that, but just in case the computer might be picky, we'll distribute the 1/10. So the final answer is 1/10 natural log of x to the 7 plus 1/10 natural log of x to the 5th plus 7. Again, this we cannot combine, okay? This is x to the 5th plus 7. We leave those alone. That's as a whole. That's together, okay? All right. Let's work inversely now. Let's, instead of expanding, let's condense. So your homework says condense the expression to a single quantity, right? So the first thing you have to know or check when we're condensing, we have to condense only logs that have the same base. So in this particular problem, we have the same base for both. They're both a log base 6. So I can use my quotient rule. So the quotient rule says that when you have two logs and they're being subtracted, the same thing as dividing, right? Oh, but first, before I do that, I have a power rule that I have to apply. Whenever you see numbers, we have to take care of those first. Okay, so whenever you see numbers, apply the power rule. So this 9 is being multiplied to the log of base 6 to the x. So rewrite this as log of base 6 to x to the 9th. Now I can apply my quotient rule now that I have single logs. Apply my quotient rule. My answer is going to be log of base 6 of 3 to the x divided by x to the 9th. All right. So, and then we can simplify. Again, we can cancel one of the x's. We can get log of base 6 of 3 over x to the 8th. All right, let's see. Let me go through this quickly again. We tried to give you a lot of information because, again, we are in summer. Even though I'm not going to get to go through everything that we have presented to you, keep in mind that these sessions are recorded, and if you want the full slides, all you have to do is contact us and we can send these to you, okay? So let's go. Let's look. Let me see if we can. We've solved some of these. Again, you can use the one-to-one properties to solve these. Oh, the B is interesting. Okay, I see students struggling with this. If we are solving for B, so we solve for x. Natural log of x minus the natural log of 13 is equal to 0. Believe it or not, this is an easy one to answer. All I'm going to do is I'm going to move the natural log, one of them, to the other side. And I'm going to do that, I'm just going to move the minus natural log of 13 to the other side. And I do that just by adding the natural log of 13 on both sides. So when I do that, I get the natural log of x is equal to the natural log of 13. And hopefully you see that, oh, now this is easy to answer for x. It's the one-to-one property. For these two logs to be equal to each other, x has to be 13. Yes? So again, I wanted to do this one because, again, it could be a little bit weird, but very easy to do. E again, I can multiply both sides by multiplying by its inverse. If I multiply the inverse of e to the x, that's the natural log. So if I do that to both sides, again, the left side, the natural log of e to the x, the answer is just going to be x. So the answer here is just going to be the natural log of 13. And to get that, we can use our calculator, plug it in. Again, just rounding the number to the thousands place, we get 2.565. All right. How about this one here? We have, again, if they're asking us to solve algebraically, again, we can use our one-to-one property for these two exponential equations to be equal. That means my exponents have to be also equal. So that means that x is equal to x squared minus 6. Again, we're left with a quadratic. We can factor it out, and we'll see that x could be equal to 3 and negative 2. And you always want to check your answers. You want to make sure that they both satisfy the equations. Let's look at these. These are interesting. I'm solving for x. Let's do a first. So to do a first, we need to isolate the exponent. So the first thing that I need to do is I need to divide both sides by 5 so I can have the exponent by itself. So when I do that, if I divide both sides by 5, I'm going to get 3x is equal to 4. Okay. So again, what I can do is I can use my properties of logs to be able to solve this. So if I multiply both sides by the natural log, okay, again, what I'm going to do, this is applying the power rule on the left side. It's going to be x times the natural log of 3. Divide both sides by the natural log of 3. So x is equal to the natural log of 4 divided by the natural log of 3. Again, now I can use my calculator, plug it in, and I think we have the example of that. Again, when I do that, I get x is equal to 1.262 rounded. Yes? All right, again, I have 7 more minutes. I'm going to try to cover a little bit more of these. Again, B, here solving for e to the x, the first thing I need to do is I need to isolate that exponent. So let's go ahead and add 9 on both sides. So when we do that, we're going to get, oh, there's a typo there. That should have been 45, not 27, right? We're adding both sides. So let's see. Let's go ahead and skip that one. There's a typo. Oh, see, it was written at the end. It was written correctly. That's what should be my answer. X is equal to natural log of 45. Okay. The other slides were the previous non-corrected. So X is equal to 3.807. All right. How about this one? Natural log of X is equal to -4. So one way to do this is, again, using my inverse property. Take the convert it into a log and then convert it into an exponent, and it's easy to see. Again, so I can do this, right? The natural log of x, I rewrote it as a base, right? The log of base e of x. These are the same things. And then I just converted it into an exponential form. E to the -4 is equal to x. This allowed me to use my calculator. Same thing with these, right? If I want to do these, what I would have to do here, first convert it into an exponential form. So again, my base is the natural log of the base is the e. So the output of the exponential is the input of the exponent, e to the 2.x. The input of the log is the output of the exponent is equal to 3x. Okay, divide both sides by 3. So x is equal to e to the 2.8 divided by 3. Again, I use just my calculator, and that's going to give me my answer, 5.482. Same thing with b. Again, I want to isolate my log. So first thing I'm going to do is going to subtract 5 on both sides. It's going to give me -5 natural log of x equals to 6. Then I'm going to divide both sides by -5. And that's going to give me the natural log of x is equal to x over -5. Now we can change it to an exponent. So the base is e. My output is 6 to the -5 equals to x. Again, use my calculator again, and I'm going to get 0.301. Yeah. All right, got 4 more minutes. Let's see if we can. Let's do one more. Let's do B. That looks a little bit more challenging. All right, let's see. All right, so we're doing B. So what I would do in B is I'm going to use some of my properties to condense and make my life a lot easier. So I see the right side, I have 2 logs that are the same and they're being subtracted. I'm going to use my quotient rule. So this is going to give me the natural log of x plus 9 is equal to the natural log of x minus 6 divided by x plus 6. Now you can see that I can use my 1-to-1 property. For these 2 logs to be equal to each other, then that means that inputs have to be equal to each other. So I'll just put the inputs equal to each other. So x plus 9 is equal to x minus 6 divided by x plus 6. Multiply x plus 6 on both to get rid of the fraction. This is going to give me x plus 9 times x plus 6. Go ahead and do FOIL. Okay, you see we're going to end up with a quadratic. Move everything to one side to combine all of our like terms and simplify. Okay, and we're going to get this x squared plus 14x plus 60. Again, we can factor or use our quadratic equation. This one is a good example to use our quadratic equation. Again, our quadratic equation is minus b plus or minus b squared minus 4ac all over 2a. Again, in our problem, a is 1, b is 14, c is 60. Plug in those values, and you'll notice we're not going to get a solution, right? Because the square root of -44 will give us imaginary numbers. Even though we know how to handle those, on these particular problems, we will have no solution. Okay, so I guess this is all for me for today. I thank you all for joining us. Please stay tuned. Hope to see you next week. Have a good weekend. and have fun. Thank you all.
Thank you, Mr. Carizales, for your presentation. We do want to remind you all about our previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist later today. Also linked is a short survey to help us improve our TVE sessions. Please take a few minutes to fill that out and remember to send your student ID number to Ms. Patricia. She sent individual messages to everyone to sign you all in today. Before you all leave, I want to share the TVE presentations that we will have next Friday. Okay, so next Friday on the 24th, 1314 will cover matrix operations, inverse of matrices, and determinants, and 1324 will cover sets, probability, permutations, and combinations. Thank you all for coming in today. We hope you all have a lovely weekend. If anyone has any questions, feel free to use the chat box or your mic. We hope to see everyone again next week for Happy Math Hour. Bye. Thank you, Mr. Carizales.
My pleasure. My pleasure. Yes. No, no
Yes,
worries.
no, no. Thank you.
Thank you. Patricia headed out a little earlier, but she said that she was able to get everyone signed in, and I think they're still finishing up for 1324.
Awesome. Good. Good. All right. I think next week Yvette will cover that one,
Okay.
but we'll let you guys know. But thank you
All right.
all. Have a good weekend. Thank you for all your help.
Thank you.
Thank
You as well.
you, Mr. Carizales. Well, we'll see you next week, okay?
Yes, ma'am. All right. Bye bye, y'all.
Thank you, sir.
Bye. Take
Bye-bye.
care.
Was the bye really that bad?
Boy, and now it sounded like